So you can, in a probabilistic sense, find after training, because it's a probabilistic machine. So this graph here is an actual experiment, and these simple kind of architectures and problems with only three. These are, say, the visual units. We have three visual units, and we have a hidden unit in a simulation in which we have a hidden factor, a hidden real causal factor. And after training, you find stuff like this. We have an estimation of this probability distribution for the hidden number of variables, and we have a salient probability for the existence of. And this cannot be done in a deterministic fashion. You need a probabilistic machine, and it's better to do with closed loops. That's more or less the idea. So we don't say that you cannot. In fact, I don't believe that you can solve it exactly, but it's maybe in a probabilistic sense true. Yeah. So we are working with this kind of problems. Actually, currently we are trying to finish this color sample, but other that is now done is this kind of. This is what usually people talks what people means when talks about unsupervised learning is maybe problems of this kind in which we have to complete a pattern completion, or maybe noise reduction and so on. For instance, we have performed this one in which we have a samples from the MNIST dataset. The MNIST dataset is I have not defined it. It's just a dataset of very simple 28 by 28 pixel images of handwritten numbers. And if we make perturbations on that, the Boltzmann, full Boltzmann machine is capable to go back to the actual basin of attraction in which the number exists. Okay, and this is the final part of the talk. I don't understand much of this stuff. So my intention also with this kind of lectures, this is the third time maybe I had given this talk 2 times in Mexico, and this is my first time out of Mexico. And my intention is to find people maybe interested to go beyond the pure algorithmics and go to the physics of the question and the electronics of the question. I know that nowadays it's possible to have chips. We have components, electronic components named memory stores. I don't know how this word is pronounced. Memory stores, maybe the meaning is because they have memory. They are capable to, because due to hysteresis effect, this kind of electronics is capable to perform memory, to have memory in the operations. And there's people that are past year, and this is a not so old article, they have used this kind of memory stores to solve optimization, discrete optimization problems in the NP class in very fast time, it seems polynomial time. But these are special purpose machines. These are just at the very beginning. I'm not sure how they work, but I am aware that this is being done. And this is an actual kind of statement, that also recent statement in the communications of the ACM, in which the authors talk about the necessity to explore this kind of computation that is similar but not the same, like computing, quantum computing. This should be a kind of thermodynamic computing by the means of these electronics or others, I don't know, maybe others, yet to devise, in which the idea is not to freeze the fluctuations and not to average out the fluctuations, but to live with the fluctuations like in our own computing machine inside of our head. So that's it. That's the idea. So I hope that maybe someone is interested in this kind of interdisciplinary collaboration in order to solve the problems, not in the way that Don Quixote solved the problems, but in a more collaborative fashion. And that's it. I know questions.
So, there are questions, comments? I have to say I have understood not so much of all this, so I would like to discuss with you, say,
Sure.
more in detail.
No, everybody's invited to do that at
so
any time.
you mean that actually there are the promises of physical devices able to implement the Boltzmann machine?
It seems so, at least in a particular fashion, yes. Yeah, they are constrained in these satisfiability problems only, and just a particular instances of that problems. They use this Boltzmann machine. When you use it for optimization, it more or less works like the training data will be actual solutions for the satisfiability problem, and then you learn how to perform the satisfaction. But these are particular instances of particular optimization problems. At this stage, I believe it is the question. I don't know if at the quantum computing level they have done something like that. I'm not sure. I know that theoretically you can solve, you can approximate the non-deterministic Turing machine by a quantum computer, but I'm not aware if they have done that in an actual circuit. They have qubits and so on, but to solve actual NP problems in the NP class, I'm not sure. I don't know actually.
Because so for what I remember, the idea is that for NP problems, no?
Yeah.
Non-deterministic polynomial problems, that you have essentially a tree of solutions that clearly grows exponentially, not with the size of the system. Each solution can be checked in a polynomial time.
Yes.
So if you have a solution, I can check it if it's correct in a polynomial.
Yeah, that is correct.
But since there are many of them, you need a kind of all infinitely forking machine in which you can, so each branch, you fork the process and you follow in parallel all of these. So in principle, this could be done by a quantum computer, clearly with all the problems of, say, temperature limitation, so fluctuation. But here you say that such problems can be also solved by a stochastic machine.
Yes. In fact, that was the original proposal by Turing. Turing, in order to prove all his theorems, he devised this imaginary, perfect, non-deterministic machine capable to explore all the branches, and that's a theoretical concept only. But it was not quantum; it was a kind of classical stochastic process.
So instead of entanglement, you have like correlations. That's the trick.
You in some way you can explore all the branches at any given time, but this is just a logical concept.
Okay, but like.
No, in a stochastic process you cannot do that. You cannot do that. you must fluctuate in order to make explorations. Yes.
Okay. So you save time because if you measure something, you know that there has to be also other kind of operations. So you can
Yeah.
He used like classical entanglement.
More or less, yes.
So yes, so what I understand, you are looking for a probability distribution that essentially is big on the real solution of the problem.
Probability distribution that represents the space of the configuration space of the solutions of the problem, and you can fluctuate among them, and you can explore in a kind of massive parallel fashion by fluctuations. That's it. And the components are correlated or connected in some sense.
Okay, so other comments or questions? Otherwise, thanks again.
Thank you. Thank you very much. And if some other questions arise, I will be at the Duce's Fanelli office at any time you wish. We can discuss.
Thank you.
Thank you very much.